When you think of spacesuits, fashion probably isn't the first thing that comes to mind. Sure, they've done their job protecting astronauts, but spacesuits also have been big and bulky and sometimes bright orange. Well, if you've been waiting for the next thing in space fashion, get ready because Boeing is about to blow your mind. Meet Boeing Blue. Boeing's new suit is designed for astronauts traveling in the Boeing Starliner, a new crew capsule that will start transporting astronauts to the International Space Station next year. Instead of the big, awkward fishbowl helmets from previous designs, the suit has hoods with pressurized zippers, which are lighter and also give astronauts a wider field of view. The new gloves also work on touch screens, which isn't available on current suits. It's totally legit. Boeing Blue is only designed to be worn inside the crew capsule, so it won't protect astronauts from hazards outside the capsule like intense radiation. But it does protect them in case there's a fire or a sudden depressurization in the Starliner. Even though today's launch suits are effective, they're also bulky, puffy, and often plain uncomfortable. But Boeing Blue is a step up. It's around 5 kilograms lighter and features more fabric around the joints for added motion. It also has fewer zippers, which means it's easier to get in and out of, and the fabric keeps the suit at a cooler temperature too. Also, let's be honest, who wouldn't want to be seen around the launch pad in one of these things? Like, I don't want to go to space, but I do want to walk around a rocket wearing this suit. But at the end of the day, Boeing Blue has to do more than just look cool. It has to keep the astronauts safe. Before they're certified for launch, the suits will undergo extensive testing to make sure they can withstand even the toughest emergency scenarios. But if all goes well, we're going to have some seriously cool-looking astronauts. Back on the ground, 2 new studies from the journal Nature are helping us answer questions about how the Earth formed, how we got our water, and how we got the moon. Until now, scientists thought the Earth was made from lots of different kinds of meteorites, including water-packed meteorites called carbonaceous chondrites. We used to think that these watery rocks showed up right at the end of Earth's formation, where they delivered most of our water in a big rush. This theory wasn't perfect, and it also didn't explain the moon. Most astronomers think the moon formed when a huge Mars-sized rock crashed into the Earth. Now that makes sense, but it also means the moon should have a different composition than our planet. It should look like a combination of Earth rocks and rocks from the impactor. But it doesn't. Earth and the moon are made of almost exactly the same stuff. But according to these new studies, the Earth wasn't formed by all these carbonaceous chondrites and other meteorites. Instead, it was mostly formed by meteorites called enstatite chondrites. These rocks get their name because they are high in the mineral enstatite, which is magnesium, silicon, and 3 oxygen atoms. They're also pretty rare. We only have around 200 samples. To figure out what was around when Earth formed, the researchers looked at the ratios of elements and their isotopes in Earth's rocks. Isotopes are just the different forms of an element that have different numbers of neutrons in their nuclei, and different kinds of meteorites have different ratios of these isotopes. We've known since the 1970s that the ratio of oxygen isotopes in Earth rocks is especially similar to enstatite chondrite meteorites. But even though the ratio of oxygen isotopes is the same, if you look at the other elements in Earth rocks, the proportions don't match up to enstatite chondrites. So scientists didn't think the similarity in oxygen isotopes was all that important. But now, thanks to recent developments in our understanding of geology, both studies were able to more accurately determine the kinds of meteorites that formed Earth. And the evidence points to most of them being enstatite meteorites. The first paper by a geologist at the University of Chicago also suggested that the meteorite's composition may have changed on Earth's surface as our planet evolved. That would explain why the elements in enstatite chondrites don't match Earth rocks today. It's awesome that we figured this out, but since enstatite meteorites are so rare, it also means we don't have a good sample of Earth's building blocks, at least not yet. And according to the second study by researchers at the University of Munster in Germany, since those water-rich carbonaceous chondrites most likely didn't contribute as much to our planet as we thought, Earth's water also probably didn't get here in a rush at the end. Now that we know that there were probably enstatite meteorites instead, which are dry rocks, it's more likely that the water appeared gradually. And if that wasn't enough new information about the Earth's history, enstatite chondrites are also helping us understand the moon's formation. The University of Chicago study suggests that the impactor that crashed into the Earth wasn't just made of random materials. Instead, the impactor and Earth probably all formed from a collection of the same materials, many of which were enstatite chondrites. So when the object crashed into Earth, it was just a big enstatite explosion, and some of the debris condensed to make the moon. If that's what happened, then it totally makes sense that the composition of moon rocks and Earth rocks would be really similar. Who knew that learning about one type of meteorite could teach us so much? Thank you for watching this episode of SciShow Space News. news, and especially thank you to our patrons on Patreon who make this possible. If you would like to help support this show, you can go to patreon.com/SciShow, and for the latest space news every week, go to youtube.com/SciShowSpace and subscribe. But this new satellite would give us about 5 days of warning because the ESA will probably put it in a spot called L5, one of Earth's